Thanks for returning. If you are visiting for the first time, you're welcome. So it's nice to know that you're there. Today I will be handling an integral part of organic chemistry, and also it is applicable in inorganic chemistry, and that is hybridization in chemistry. You know, there is hybridization in biology, but the one I'll be discussing in this video is hybridization as it concerns chemistry. So first, you should know that hybrid is just a product from two things that are not the same, whether in biology or in chemistry. So it's a kind of mixing, the product of mixing two unlike things gives you a hybrid. So in this aspect in chemistry, you will write the topic first, hybridization. First, by definition, hybridization is the mixing or the overlapping of atomic orbitals to produce hybrid orbitals or molecular orbitals. These hybrid orbitals are actually similar in energy and shape, and they are suitable for formation of covalent bond. Remember, this hybridization is very important and necessary in organic chemistry, like I said earlier, because it enables carbon to exhibit tetravalency and gives carbon its ability to form bonds of nearly equal strength and length. So in hybridization, it's all about blending of atomic orbitals of different shapes and slightly different energies to produce hybrid orbitals of similar shape and energy, such that they will be suitable for formation of a covalent bond. Remember, we will be dealing with the orbitals, and when we talk about orbitals, you can also see them as subshells, and you have the s orbital, the p, d, and f. That's s, p, d, f. And the s has a different shape. For example, you have s is spherical, p is dumbbell, then d is actually double dumbbell, kind of twisted in this form. So this is, let's assume if you come to an atom that have electrons found in these orbitals of different shapes, you cannot use them in covalent bond formation until they are hybridized, until they are mixed to produce an orbital of uniform shape and energy. So the main aim for hybridization is to ensure that there will be formation of bonds of equal length and strength by different orbitals of different shapes, such that when you see a molecule containing a bond from S and a bond from P and a bond from D, likely, you will know the difference. They will be of the same length and equally same strength. Okay, therefore, having defined hybridization, let's take a look at first that of hybridization in carbon atoms. When we come to hybridization, you need to know the ground state electronic configuration and the excited state electronic configuration of an atom in consideration here. Take note, when I say ground state, it means the electronic configuration of the atom when the electrons are found in their natural state, in their natural energy level. There is no promotion or demotion. That is, where they are occupying their normal quantum number. There is nothing like pushing up or pushing down. So when the electrons of an atom are usually found in their normal state, natural state, we say that the electronic configuration is in ground state. But when you push one electron from lower energy level to a higher energy level, if you write such electronic configuration, you say that it is electronic configuration in excited state. Supplied energy, remember what we call energy level, is actually shell, KLM, and it is also applicable to SPEF. They are sub-energy levels also. So let's take a look at the hybridization of carbon atoms. We are looking at the hybridization of the orbitals of a carbon atoms. First, carbon is number 6. That's the atomic number. So let's take a look at the electronic configuration of carbon in ground state. So carbon is 6, which means we have 1s2, 2s2, 2p2. That's 2 plus 2 plus 2, which will give you this 6. If you don't know how to write this electronic configuration, check other videos here on this channel where I taught you the easy cheat on how to write electronic configuration. Within a few minutes, you'll be a master on that. Okay, let's proceed. Having seen this, we are now converting it into lobe. Remember that S orbital has one lobe. Take note. S has one lobe. P has 3 degenerate orbitals or lobes. Then D has 5. 2, 1, 2, 3, 4, 5. Then F has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's the number of subshells you will divide in each of them. If you want to use the acronym, you can start with SPDF, start with 1, add 2. That's start with 1 and add 2 successively. So this means SPDF, 1 lobe plus 2, 3 lobe, 3 plus 2 is going to give you 5, 5 plus 2 is going to give you 7. So these are the suborbitals or the degenerate energy levels or degenerate orbitals present in each subshell. Now, I want to represent this. This is 1s, 2s, 2p. So because this is s, I only drew one lobe or one degenerate orbital, and there are 2 electrons there. That is spin up, spin down. Then here, we have the same thing, up, down. Then remember this is p, it's no longer s. So how many will p be? P will be divided into 1, 2, 3, no longer 1 room. So I'm going to divide this. And remember, what I'm showing this is, can't you see, I'm taking a step, meaning that 2s is a little bit of higher energy than 1s, whereas that of 2p and 2s are slightly of the same energy, but 2p is slightly higher. So that's the step we are seeing, not just that it's a step. Therefore, we have 2 electrons here. I will not put the whole 2 here because this is against the Aufbau and equally the Pauli's exclusive principle and your Horn's rules. So remember your principle, your quantum numbers. So what is required is that before pairing will start, I have to write 2, 2. So in this case, this is the electronic configuration of carbon in ground state. Then, before I proceed, take note of this. In a covalent compound, let's assume this is X bonded to X, and this is also Y bonded to X, whichever. If this is a covalent bond, and there is another covalent bond, each covalent bond is formed by 2 electrons, which means one will come from this participant and another one will come from this participant. Which means if you have one single bond connecting 2 atoms, it means that 2 electrons are involved, whereby the other participant provided 1 and this one provided 1. But if you have double bond here, how many electrons forms double bond? 1, 2, 3, and 4. Because I told you that one covalent bond is formed by 2 electrons. But that 2 electrons will not be contributed by one atom. Rather, it should be one from one atom and the other from the other atom. Remember your covalent combination. So, what I'm trying to tell us is this. If we have a compound like this, how many bonds? There are 1, 2, 3, 4. 4 covalent bonds. It means that carbon has contributed how many? 1, 2, 3, and 4. And each hydrogen here also donated in the formation. Which means for carbon to form this type of compound, carbon is supposed to have orbitals that have up to 4 unpaired electrons. And when you come to orbitals, orbitals with unpaired electrons are the orbitals used for covalent bonding. Don't confuse coordinate covalent bonding with covalent bonding. Orbitals that are singly filled are what atoms use in covalent bonding. So when you check this, we have only 2 unpaired. And in this case, carbon can only form but 2 covalent bonds. You cannot use this one because it's paired. As I told you that when you come to one bond, there are 2 electrons forms it. And that 2 must not come from one participant, which means this orbital is no longer qualified for formation of covalent bond here, since it already has 2. Rather, this one that have 1, 1 is what will participate. So in this state, this compound, carbon cannot form this compound in this state. Therefore, what's the valency of carbon here? Valency of carbon can also be detected by the number of unpaired electrons. So which means in ground state, carbon is divalent. Di means 2, meaning carbon is plus 2. This is the electronic configuration of carbon in carbon 2 oxide. That's the only thing carbon can form here. And also in a kind of, I think, the methylene group, a situation where we have something like this, the carbene. So CABNE, carbon is plus 2 in that case. But in all organic compounds, carbon is usually plus 4 and not plus 2. So what must happen to enable carbon form 4 unpaired electrons? There have to be what we call excitation. So the simple thing there, so remember there are things here. 1s is the first shell, that's the 1, but these 2 are in the second shell. Remember carbon KLM, carbon is 6, 2, and 4. These 2 are here, are all in L share, and hence that's why they are bearing 2. But this K here is in the first shell. So these ones, remember, the electrons of the inner shells in chemistry do not participate in bond formation. Therefore, it is these last 2 that will participate in bond formation. But as we have seen, that out of these 4, 2 is in S and 2 is in P. And by drawing it or showing this at ground state, it is divalent. So let us see II, this should be I for carbon, II, electronic configuration of carbon in excited states. Now, remember I told you that SPDF, that's the order of energy. S lower than P, P lower than D, D lower than F. That's the energy level. So if I shift electron from S to P, it is called excitation. But if I shift electron from P to D, it is called demotion, and that should be emission. This you will learn this when I teach about emission of spectral line and the atomic theories in details. But just know that excitation means shifting an electron from a lower energy level to a higher energy level. So let's go. Coming here, we have 1s2, 2s2, then 2p2 as usual. Now, permit me to divide this to x, y, z, to use x, y, and z to distinguish between these three sub-degenerate orbitals of p. So what will we have? We will now have that this is one block, up, down, up, down. Then, instead of having 2p, 2, I have to make it clearer. I will now make it 2px for this first, 2py for this second, and 2pz for the last one. Remember, it's just x, y, and z to distinguish, which means this one will be 2x1, because there is one there, 2py1, and 2pz0 in ground state. But in excited state, watch this. I want to shift. In excited state, it involves shifting one of the electrons in the 2s to occupy the vacant 2pz. So, and that's what we call excitation. And immediately if I do that, I clean this remains 1, and that electron comes here. So in this case, the electronic configuration becomes now 1s2, 2s1, because one of the electrons here has been promoted to occupy the vacant 2pz. Therefore, we have 2px1, 2py1, and 2pz1. So watch this. I told you earlier that the orbitals with unpaired electrons are the orbitals qualified for covalent bond formation. If you check an atom, if you check carbon atom now, there are 1, 2, 3, 4. These are 4 unpaired electrons, which means in this state, carbon is tetravalent. Tetra means 4. So in excited state, carbon is tetravalent. And carbon has how many orbitals now qualified for bond formation? It has 1, 2, 3, 4 in excited state. Unlike in ground state, where there is only 2 lobes in the 2p orbital available for covalent bonding. But here we can see that 2s is now available, 2px is available, 2py is available, and 2pz is also available. So this is why carbon exhibits tetravalency in all organic compounds, and this enables carbon to form methane, as I drew before. Now, at this juncture, this is where you now understand why we need hybridization. Here, hybridization is not actually necessary. Why? Because it's of the same shape. This is pp, these two orbitals are of the same shape, and they belong to the same energy level. So they have similar shape and similar energy. But watch these, 1, 2, 3, 4. Out of these 4, 3 is in P, and 1 is in S. And remember, S is spherical, and P is dumbbell. So imagine using these 4 to form bonds. It will give you bonds of not equal length and strength. Therefore, there should be a need to harmonize, to make them uniform, to make them overlap, and look similar in terms of energy and shape. And that process is what we call hybridization. So in excited state, there are 4 orbitals in carbon atoms available for bond formation. And this enables carbon to form such compounds as carbon 4 oxide, because it is now tetravalent. Then in all organic compound, carbon is tetravalent. Now, let us see these types of hybridization using this carbon. Types of hybridization with reference to what I explained now. Types of hybridization. The common types is what you yourself will now know. Having seen that over here, we have the S, 1s orbital, then we have the 3p orbitals mixing together. Just watch this. What if this one and this one blend or overlap? We call it, that's bringing one S. Let's call it S1 and P1, meaning one of the S and one of the P. that will give you S1P1, and when 1 is involved, you remove it and just call it SP. So in that case, when 1,2s orbital mixes or overlaps with 2px, we call it sp hybridization, leaving y and z unhybridized. Therefore, what if this s mix with 1, 2? Therefore, we have 1, 2, 3 mixed up. That should now be s1 and p2, meaning there are 2 p orbitals mixed with 1s. And if this is 1, you remove it and call it sp2. Then what if 1, 2, 3, 4, all of them mixes up, overlaps? It becomes S1 and actually P3. Then 1 is there for nothing, we now call it SP3. So I've indirectly taught you now the 3 common types of hybridization with reference to carbon atoms. So there are SP hybridization, SP2, SP3 hybridization. In SP3 hybridization in carbon atoms, all of the orbitals are hybridized. Why I didn't touch this is that it's in the inner shell, remember, it's in the K shell and do not participate in bonding. Remember in chemistry, the valency electrons are the electrons in the last shell or the outermost shell, which is this 4 I'm talking about. So the 3 common types, I'll teach the other advanced form, but the 3 common types of hybridization are SP, SP2, and SP3 hybridization. They have their own common name and shapes. But before I go further, why must we study hybridization? Apart from that, this enables orbitals of different shapes to form bonds of similar strength and length. Hybridization enables us to study the shape of molecules. So in molecular geometry, hybridization is very necessary. Even in stereochemistry, study of structures, hybridization determines the shape of molecules. Hybridization of the atoms present in a molecule determines the shape. As we can now see, in this 3 types of hybridization, having seen that SP, meaning that 1s mixed with 1p, we call it SP hybridization. This is now the hybrid orbital. And there are unhybridized, there are 2 unhybridized orbitals. Therefore, how can they be distributed in this case? Now, there should be something I want us to know before going further, please. There is what we call sigma bond and pi bond in this aspect, because watch me, I mentioned about those that mixed or overlap, they are the hybridized, then those that did not hybridize in this case. The ones that are hybridized are used for sigma bond formation, for hybridized orbitals. They are used for sigma bond formation or sigma hybrid orbitals. Then the unhybridized are used for pi bond, or you can use the mathematical sign to represent it. Pi bond is for unhybridized. Sigma bond is for hybridized. Then sigma bond is a very strong bond, while this one is a weak bond, or rather is weaker than sigma bond. And this can be broken by addition reaction. Addition reaction do not create sigma bonds. I repeat, sigma bonds are formed by hybridized orbital, while pi bonds are formed by unhybridized orbital, or rather by the overlap of the orbitals, which are actually the hybridized one, along the axis. If this is an atom, and this is another atom, and this is another atom, if there is atoms overlapping, connecting the 2 atoms in the major axis, in the central axis, we call it sigma bond in the straight line. But lateral overlap is pi bond. Take note, pi bond is only present when there is more than 1 covalent bond between 2 carbon atoms, or between any atom. Sigma bond is only present when there is only 1 covalent bond. See what I mean? If I have C bonded to C, this bond here is sigma because it's in the central part. But if there is another double bond, that's lateral, sideways, not in the middle, not in the central part, that is pi bond. So if you have double bond, there is 1 pi bond and there is 1 sigma bond. Then if you have triple bond, which is the maximum for carbon to carbon, there is 1 sigma bond and 2 pi bonds. So these ones on the side, these ones, the lateral overlap, they are the pi bonds, while the central one is the sigma bond, and they are formed mainly by these ones that are hybridized. Then these 2 that are not hybridized are what is now used for this lateral overlap. Now, let's take a look at, after the hybridization, we just assume that the product of their hybrid is in this form. Watch this. This is what is obtainable in the sp hybridization. You see here, this is the hybridized orbital, this is the hybridized. Then these two, remember this is the carbon atoms we are talking about. This one that is unhybridized will now overlap. So in this central overlap, this is the sigma bond, and here is the pi bond. The central and over. Then this one is unhybridized, this is unhybridized, and these two are actually the ones that are hybridized. Remember, they can now use this one to form another bond, because this is assumed to be one carbon, and this is assumed to be one carbon. Here can now, that is where hydrogen can now come in. Hydrogen can come in here, but these two are this 1, 2, remaining unhybridized. So unhybridized orbitals are used for sideways overlap, and they lead to the formation of pi bond, which are weak bonds. Then overlap along the axis, connecting the atoms straight, not on the sideways of the atom, is called sigma bond, and they are formed by the orbitals they are formed actually by hybrid orbitals, and that is a strong bond. Now, back to this, what we are saying. Having explained this, another name for sp hybridization, it can be called linear hybridization. Some may decide to call it linear hybridization because of the arrangement of the molecules formed from this type of hybridization. The only possible way to make them distributed is that they usually appear in a straight line form, that's linear. Then sp2, and when we say linear hybridization, take note, the bond angle here is 180 degrees Celsius. Since it's linear, remember angle in a straight line is 180. Then sp2 in such a manner that there is a kind of arrangement in a plane triangle like this. This is the central carbon atom. Remember in sp2 there are 3 hybridized, 1, 2, 3. So those ones there are distributed in this way. So, and forming a triangle, therefore, is trigonal planar. So some might call sp2 trigonal hybridization, and the bond angle is 120 degrees Celsius. So in sp2 hybridization, the bond angle is 120 degrees. The bond angle is 120. So that is for sp2. Then sp3 means 4 orbitals, 1s and 3p, combining to form. So the spatial arrangement, the way these particular bonds should be arranged to have equal distribution, because since they hybridize, it means they have equal repellence. They will repel each other at equal distance and equal angle. The only distribution is that they have to be distributed to form a tetrahedron. More of this, as you can see in methane. So in this aspect, sp3 hybridization is called tetrahedral hybridization. This is linear. sp2 can also be called trigonal planar. Then sp3 is called tetrahedral because the hybridized orbitals, or the hybridized orbitals, of course, are spatially arranged such that they point towards the corners of a tetrahedron, while this one points towards the corners of a triangle, such that the bond angle here is 120. Then here the bond angle is about 109.5 degrees. So in sp, hybridization is linear, is 180. That's the bond angle. In sp2, the bond angle is 120 and is a kind of arranged in a plane triangle, in a right angle triangle, of course. Then in that of sp3 hybridization, this is called tetrahedral hybridization because of the spatial arrangement of those bonds at the corners of a tetrahedron, and this determines the shape of molecules. So any molecule that have sp hybridization, the shape is going to be linear. Then sp2 is going to be trigonal planar, trigonal pyramidal, within that trigonal. But most of them that are sp3 hybridized are tetrahedral in shape. Like I told you earlier, that one of the reasons for studying hybridization is to study the shape of molecules, and it's coming out now gradually. Now, if you have not subscribed to this channel, do so, because this channel has a lot of things to offer you. I work every day for your academic success, so you should also work every day for the success of this channel. I cannot do without you. Science is fun and is good when you are taught well. So spread the light. Much love. Remain majestic. Back to what we are saying. Okay, now let's bring this down to a way that will help us answer some questions in exam. Sometimes you'll be told what type of hybridization is found in a given compound, and that is an organic what? Compound. Simple. Just take a look at the secret. Okay, we have seen sp3, sp2 hybridization, and sp hybridization. This is 3, 2, 1. Then watch me. I'll just draw carbon, 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 carbon. I counted 3, 2, 1. I'll do the reverse this time around. Just wait and you understand the reverse I mean. 3, 2, 1, and the reverse of 3, 2, 1 is 1, 2, 3, which means 1, 2, 3. Simple. So any compound that have carbon to carbon single bond throughout is sp3 hybridized. And such compounds, if they are hydrocarbons, are called alkanes, or you can call it alkanes. Then these ones that have double carbon to carbon bonds are nothing but what? The alkenes, and they are sp2 hybridized. Then in the presence of a triple bond makes the molecule nothing but what? Alkynes. So the alkynes or the alkenes or alkynes, these alkynes are sp. So the carbon atoms in alkynes are sp hybridized. The carbon atoms in alkenes are sp2. The carbon atoms in alkanes are sp3, which means if I ask you what type of hybridization is found in methane, AN is simple, sp3. Then what type of hybridization is found in, let's say, propene, ENE, nothing but sp2, because it's the ene there. Double bond is for ENE, single bond is for ANE, triple bond is for YNE. That is it on how to answer questions concerning hybridization of carbon atoms. Then, if you have a compound like this, watch this. These have both single, single, and double. In exam, if you see such molecule and they ask you what type of hybridization, simply answer sp2. If there is one double bond, it dominates other single bonds. So that doesn't mean, if you see another one like this, the type of hybridization here is nothing but sp because of this triple bond. Don't worry about this. But you can only answer when there is single carbon to carbon bond throughout. So alkanes are sp3.
Hi, my name is Cheryl.
And I'm Jennifer.
Guess what? There's a channel called Her Majesty Easy Word Science.
And do you know the best part? It makes science so easy. Wow.
It makes science easy, simplified, and very, very fun.
Guess what? Rocket science ain't rocket science anymore.
It's now ABC.
Like if you did science your entire life.
Another thing about Her Majesty Easy Word Science channel is that he makes available laboratory equipment and reagents.
Guess the best part? If chemistry has been hard for you, he does tutorials.
And another thing is when you order for these things, they are high quality and they are also cheap and affordable for anybody.
If you want to order, just look at the number below the screen.
And don't forget to subscribe and hit the little notification button down below.
Don't forget to share, of course, obviously there's love in sharing.
Thank you! See you there.
The whispers in the morning.
Why the alkanes are sp3, alkenes sp2, alkynes are sp hybridized. Okay, now this is it for normal and common three types of hybridization. Let me now take you a bit higher to where d orbitals participate in hybridization. You know, theoretically, if you have gone higher in chemistry, d orbitals, because of the large shape and the higher energy, it becomes almost like theoretically impossible that they can mix with S and P. But I'll show you conditions where d orbitals can participate in hybridization, and that will take us to other types of hybridization apart from sp, sp2, sp3. This is when d orbital comes in. So hybridization involving d orbitals. Now, in hybridization involving d orbitals, take note of this. We are no longer looking at organic compounds here. Inorganic compounds also coming into this. So hybridization, remember, is not only for organic, but it's an integral part of organic chemistry. But that doesn't mean that some molecules that are inorganic, that the atoms there do not undergo hybridization. No. So, but when we talk about d orbitals, hybridization involving d orbitals, your mind should no longer lie only on organic compounds. Okay? Then, remember the energy level for this subshell SPDF. That's the increase in energy, which means F is of the highest energy, followed by D, then S and P are of the lower energy. Remember in hybridization, orbitals that have far higher energy between themselves becomes very difficult to hybridize. They don't overlap. S and P are close enough. Their energy levels are a bit close, such that they can mix. But D, the energy of D is high. Why? Because of the large size of the orbital. So energy of an orbital is directly proportional to the size of the orbital. Take note, is the energy of an orbital is directly proportional to the radial distance of the orbital. Which means if an orbital, for example, is assumed to have this shape, another orbital have this shape, this one that is larger have higher energy, this one that is smaller have lower energy. Therefore, the shape of D is very far, is large, therefore the energy is also large. So nobody will be expecting that normally that D can blend well with S and P, but there are conditions where D can be made to reduce its orbital size, thereby lowering its energy to make it possible to do what? Hybridized with S and P. In this case, electronegativity of some atoms makes the orbital possible to participate in hybridization. First, let me take a look at phosphorus. In phosphorus is number 15 and the configuration is 1s2, 2s2, 2p6, that's 10, then 3s2, that's 12, then 3p3. Exactly, so we have 12 and 15. So by drawing this, we have this. We will start here. Remember, this 3 means the last shell. That's KLN 285. So we find out that this 5 is 2 plus 3. So they are the one that will be participating in bonding, whether it's covalent or electrovalent. But it's mainly for covalent. That's the one we are considering here. So in this case, in this class, I'm taking a look at the last shell. So don't worry about these inner shells. They don't participate in bonding in chemistry, of course. So we have this. Remember, S has only one lobe. Then P is divided into 3 lobes. And I told you I will not put 2 in one until each one has gotten 1. So because it's 3, I'll put 1, 2, 3. And there is no one remaining again. In this case, can you suggest the valency of phosphorus here? Phosphorus is trivalent. Why? Despite it has 5 here. But by this now, we show that in ground state, this what I've written now is the ground state configuration. In ground state, phosphorus is trivalent. Why? Because it has 3 unpaired orbitals. And only unpaired orbitals are available for covalent bonding. Remember, a paired orbital can only participate in coordinate covalent, but unpaired participates in covalent bond formation. Now, there's going to be excitation. As usual, there will be excited state. Remember, after SP, according to the energy, SPDF. So if you come to this shell, M shell, after S subshell, P subshell, the next subshell that should be there is D, though it's vacant. Nothing occupies it because it's vacant. But what I'm just trying to let you know is that we are going to have excitation. After S, this is 3S, we have 3P, and after 3P, there should be 3D. Yes, of course. In this aspect, you divide D into how many? I told you earlier, 5. 1, 2, 1, 2, 3, 4, and 5. This is divided into 3. Then, initially, this is only 2. We have up, down. Then this is 3, up, up, up. Then this is empty. When the excitation takes place, one of the 3s electrons will be promoted to occupy the first subdegenerate orbital of the 3D. So in this case, excitation promotes this to this, giving us now nothing but 1 here, and here is 1. Therefore, electronic configuration of phosphorus in excited stage will be 1s2, 2s2, 2p6, 3s1, then 3p3, and then 3d1, of course. By so doing, remember as usual, to make it clear that 3px1, 3py1, and 3pz1, and then 3d1. So how many unpaired? We have 1, 2, 3, 4, 5. So in excited state, this is nothing but phosphorus is pentavalent. Now, remember there is what we call electronegativity, the tendency with which an atom attracts or controls a shared pair of electrons. We call it electronegativity. So the tendency of an atom to gain electron is called electronegativity. Remember in covalent bonding that atoms contribute electrons from their unpaired orbital so that they share it equally. But in the presence of highly electronegative elements, they try to get more share of the, I don't know how to put it, watch this. This arrow I've been drawing is actually something like this. These 2 electrons. Let's assume these 2 electrons are contributed. One came from here and one came from here. They're supposed to have equal effect on this. But in the presence of highly electronegative, let's assume this is chlorine, for example, and this one is a less one, maybe hydrogen. This chlorine will tend to have more control over these 2 electrons than hydrogen. And when you gain more electron towards yourself, you become negatively charged. Therefore, this one can now acquire partial positive charge. Why? Because the chlorine is having more control over that electron. It's just like you meet 2 hungry men along the road. You discover that the other person is just telling you, I didn't eat since yesterday night, and it's almost evening day. On trying to help the person, you see someone dying, telling you have not eaten for 1 week. You know, these 2 people are hungry, but one is more hungry than the other. So in that case, the person that have not eaten since yesterday night, you overlook that person and take a look at who have not eaten for about 1 week. So chlorine, for example, highly electronegative. It has more affinity for electrons. So even though it's sharing it with the hydrogen, let me just use it in real sense because this is true. In HCl, we'll use it to understand what I'm saying. Hydrogen is 1, then chlorine is 287, so it's bigger in size. But the last share is having 2, 4, 6, and 7. Therefore, this hydrogen has only 1. It will contribute that one, like I told you, an empty orbital. Coming here, the hydrogen will pair. And this is what we call, this is hydrogen and this is chlorine. That is HCl. What I'm explaining is this. These 2 electrons, chlorine atom has more control over them. Why? Because chlorine is highly electronegative. Chlorine attracts more electrons than hydrogen. But normally what is supposed to be is that they're supposed to have 50-50 equal share of this electron. But it will be a kind of 70-30. So this one that are taking the electron closer will tend to be negative. Then this one that is allowing it to go far away is now acting to lose it, will become plus. And that's why you say that HCl can be polar, and due to this might dissolve in water, and this is very, very clear in H2O, where the oxygen have a greater control over the shared pair of electrons. Now, back to what I'm saying. Over here we have, there will be what we call hybridization, of course. So in this type of hybridization first, for you to use S orbital and P and D, remember D is double dumbbell, this S is dumbbell, and this P is spherical. So you have to blend them. And this type of hybridization, there will be how many S? S1. How many P? 3P. 1, 2, 3. Then how many D? 1. So you can call this type of hybridization in excited state of phosphorus sp3d. So sp3d hybridization is now here. Remember, I'm telling you hybridization that involves the d orbital. So we have sp3d. So with this, chlorine, when it reacts with phosphorus, it forms phosphorus 5 chloride. And this is why phosphorus 5 chloride can be formed, because this chlorine will first of all have a greater effect on the electrons, and that will now reduce the size of this d orbital, which enables it to participate in hybridization with S and P. So you have sp3d hybridization. A good example of compound that have sp3d hybridization is phosphorus 5 chloride. Then there is no such compound like this. Remember, we have pH3, an analog of ammonia. This is called phosphine, but we don't have this. Why? Because hydrogen is not highly electronegative. It won't pull this electron more, giving this phosphorus a positive charge, which now reduces the size of the d orbital. So this is why PH5 do not exist, but PCl5, that's phosphorus 5 chloride, exists. And the type of hybridization found in it is sp3d hybridization. So let us see another hybridization form of the same d orbital. Let's take a look at sulfur in sulfur hexachloride. In sulfur hexafluoride, rather, not chloride, that's SF6. So sulfur is number 16. Therefore, ground state, GS, ground state is 1s2, 2s2, 2p6, that's 10, then 3s2, that's 12, then 3p, we are sharing, that should be 4, of course, 3p, 4. Then, which one are in the last shell? 3, they are the last shell, so we have to consider them. This one is none of our business because they are in the inner shells. See what I mean? K, L, N, that's 2, 8, 6. That 6 is 4 plus 2. It is only this last shell that participates in bonding. Gain and loss of electron is only for the last shell, not for the inner shells. Okay? Therefore, we have up, down, 3s2, the same thing. P should be divided into 3. We have up, 1, 2, 3, then you come back. So in this state, what's the valency of sulfur here is only but 2. Why? Because sulfur has only 2 unpaired orbitals. In ground state, sulfur cannot form more than 2 covalent bonds. Therefore, there should be now excitation. Remember, after P, there should be D. Let us take a look at the excited state. Excited state for sulfur should now be, we are going to include the D in addition to the P and S. 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2. So now we have up, down, up, then this is empty. When the carbon atom is excited, one of the 3s electron is promoted, making it now 3s1 to occupy the first orbital in D. The same thing is applicable here. One of the 3px is promoted to occupy this. So this is how many unpaired now? This has gone off. This is 1, 2, 3, 4, 5, and 6. So in this case, sulfur is nothing but plus 6 because it has 6 unpaired. Therefore, if you are told to explain this type of hybridization, when all of them mix, information of this sulfur hexafluoride. Remember that fluorine has 7 in the last shell, just like chlorine, so it's looking for 1. So it will pair up. This is a covalent compound either. So in this case, the type of hybridization is how many S are here? 1. How many P orbitals? 1, 2, 3. How many D? So this is what we call sp3d2 hybridization. So in this case, the type of hybridization found in sulfur hexafluoride is sp3d2 hybridization, and you can see the shape. Their shape are determined by this. They also have their own shape and their bond angles, as you see there on the screen. So there are other special forms of hybridization involving the orbitals. Even the one, we have the dsp2 hybridization. There are many of them. sp3d3 hybridization. They have their own name, and these also have a shape. Their shape also varies, just like you saw in this case. So this wraps it up about hybridization. I believe that by now, if hybridization has been difficult for you, I think I've made it simple because this is the easy world of science. My job is to simplify science for you and make it work for you, and make you come out with a wonderful result, of course, in your exams. Please don't forget to share my videos. Expand this science community. I love you so much. Much love from me to you. Remain majestic.
I love you. Thank you for watching.
And